So now we are moving on in the program. Thank you so much. We are coming to our next expert contribution entitled Product Carbon Footprint of Performance Polymers. And it's my honor to welcome Gregor Daun from BASF. Gregor is the Director of Manufacturing Technologies at BASF. And he's also a very experienced mechanical and chemical engineer and a lecturer on carbon management. We are very much looking forward to your talk, Gregor. The floor is all yours. Please go ahead.
Thank you. That works? Yeah, okay,
that
cool.
Works.
And this is how I move it forward. Okay,
yeah.
Cool. So, thanks for having me, giving me the chance to talk about the range of product carbon footprints for certain performance polymers. So, the whole purpose of the talk is to create a bit more transparency in this industry. First of all, there's, over the last couple of years, a growing interest in product carbon footprints. Some customers actually advertise with it, as you can see here with the VD backpack with a 0 PCF polyamide 6 from BASF. But there's also the need to get to these data fairly quickly, which is why we use a growing number of digital platforms. So if you're a buying customer of BASF through My BASF World, you can just download the data through your account. But we also use more open channels like the Catena X in combination with our own Pacific app, or the PAC platform in combination, for example, with the Seguin software. So there's a growing number of channels to get these data from us. Also, hang on, how do I go? Also, it's important to understand that we need to calculate all of these product carbon footprints in a similar manner. And so on the right side, the earliest version is here of the Greenhouse Gas Protocol, 2011, with the first indication how to calculate carbon footprints. The ISO norm came out in 2018, but only with the introduction of the Together for Sustainability standard in 2022, we feel we have a standard for the chemical industry that if you adhere to it, you can really compare the product carbon footprints of different companies. If everybody picks their own standard, it's very difficult to compare the data. But how do product carbon footprints grow over the length of a value chain? So you start with a certain feedstock, like coal, natural gas, naphtha, and so already the initial sourcing, digging, drilling comes with potential process emissions in yellow, heat, energy emissions, for example, from coal and gas, or electricity emissions, because also the electricity is still predominantly produced with fossil resources. And so, as you move from the initial feedstock through the base chemical, to the monomer, to the polymer, to the final compound, you keep adding these emissions until you have the final carbon footprint of what we sell. But it's all built up through either process emissions, heat, basically emissions, or electricity emissions. And that's what you need to tackle. And this is where already a big difference in the product carbon footprints arises from, because it makes a big difference whether you, for example, produce your heat, for example, for steam, with lignite, like brown coal, hard coal, naphtha, natural gas, or even more, if you use fossil-based electricity, very big difference in the emissions in gram of CO2 per kilowatt hour, whether you base it on lignite, hard coal, naphtha is rarely done, natural gas. And if you take this even further, if you have a combined gas cycle plant like we have in BASF, you produce steam and electricity at the same time, and then you have extremely low emissions at around 200 grams of CO2 per kilowatt hour. So that's one of the biggest changes between, or differences between different producers and regions. But on top of that, the question is, what do you take as a feedstock? And that chart here is maybe seen less often. On the y-axis, I've just printed or taken here the calorific value. That's like the heat value of a certain material, the chemical energy. But more to this talk here, on the x-axis, we have the carbon to hydrogen ratio. And it's important to note that if we look at the products that we typically produce here, for example, polyamide 666, the carbon to hydrogen ratio is just 0.5 something. You roughly have 2 times as many hydrogen atoms in the molecule as you have carbon atoms in the molecule. And that's, so if you start with methane or natural gas as a feedstock, then it's fairly easy to get there. If, however, you come from coal, anthracite on the right side, that has a carbon to hydrogen ratio in the range of 2 to 3, fairly often above 2.5. And you somehow have to get rid of that carbon. And there are 2 ways to do that. One is basically you pimp your coal by using green hydrogen, but nobody does that. It's far too expensive so far, not on industrial scale. What happens is, more or less, you burn off the majority of the carbon to get to the right ratio. And that's why Ian Reid here says for polymers, it means that less than 1/3 of the original coal carbon is present in products, with the rest emitted as CO2. So coal is really not a good feedstock for polymers. Keep that in mind when we look at individual polymers. So the third type of emission that will be difficult or will generate a large carbon footprint is if you have process emissions, like in this case, when you go from benzene to adipic acid. Adipic acid is one of the monomers for polyamide 6,6, and in between, laughing gas is generated and leaves typically through your chimney. And because it's stoichiometric, for every mole of adipic acid, you generate 1 mole of laughing gas. And that has a high global warming potential of about 265 kilograms. 1 kilogram of laughing gas in the atmosphere is as bad as 265 kilograms of CO2. And so if you don't abate that, if you don't destroy that, that explodes your carbon footprint. And I started that discussion with my internal colleagues and said, is that an issue? And 2 years back, I was told, no, no worries. Also not in Asia, every plant has laughing gas abatement, because after the Kyoto Protocol, the UN started a program where basically Western companies could fund the installation of laughing gas abatement technologies throughout Asia and especially in China. What a lot of my colleagues did not register, that those plants were no longer running, that for new capacities, they weren't even built. So, and I'm quoting third-party sources throughout the whole documentation, today China has the world's largest adipic acid industry. We buy also from that industry. We produce, but we also buy, and we find out that quite a few of them do not abate their laughing gas emissions. And we only find that out in the last 1 or 2 years. The effect is that due to these different impacts on polybutylene terephthalate, PBT, you find technically a range of carbon footprints that's factor of 2 between the lowest and the highest. For polyamide 6, factor is 5. For polyamide 6,6, the factor is 9. And if we look at this in more detail, these numbers on PA6, again, third party, because difficult to hand out BASF numbers, also maybe you wouldn't trust me, so I'm taking data from our competitor Envalior, I'm taking data from Plastics Europe, and they match to our findings. If you get a low carbon footprint polyamide 6 in China, and we also buy that partially, we make and we buy, you're good if you have a carbon footprint of around 12. I see these data from suppliers. If you're even worse, you could go up to 20. In Europe, the good suppliers are beneath 4. Yeah? So that explains the factor of up to 20. And the problem lies in the caprolactam, the precursor. If it's produced without abatement, if it's produced with coal energy, then you end up with these high values. Same thing here, we talk about PA66. That's what I talked about before. If you do not abate the laughing gas during the adipic acid production, your adipic acid has a carbon footprint not of whatever, maybe around 3 to 4. In Europe, it has a carbon footprint of about 84. And that's pure mathematics, geometry. That's not company knowledge. You can do the simple math as I did on the slides before. And during the last 1 or 2 years, we have now that transparency that our suppliers tell us, well, actually, the adipic acid that you buy from us comes in not with a carbon footprint of, 5 or 10, it comes in with 80. We've changed our sourcing. We strive to only buy abated adipic acid, but then we do a contract with a company and we find out one plant is abated, another plant is not abated, and they are supplying us from both. So this is a really difficult thing, and I'm only urging everyone, us and everybody else, to make sure that we dig deep and ask our suppliers, how do you produce and how do your upstream suppliers produce? Final example is here, PBT, polybutylene terephthalate, is based on butanediol and terephthalic acid. BASF, our colleagues at the Intermediates Division, produce a lot of BDO. They closed several plants during the last years, and especially in Asia and especially in China, the dominant players now all produce based on coal or on coal-based acetylene. Nobody can compete with that commercially. So when I ask our own colleagues when they source BDO locally, when I say, what are the alternatives? I'm being told almost none. Frankly speaking, all the good guys have closed shop. The coal-based chemistry is so cheap that it has kicked out all the other chemistries, and it's difficult for us to find sources where we can find BDO that's based on natural gas. We find them, we buy it, we also produce some ourselves, but this is really tricky even if you're in the chemical industry yourself. And it gets more tricky because even the ones that use coal-based BDO for their PBT, they should have a carbon footprint of more than 8, but they sell it to us with a carbon footprint of 4, and the carbon footprint is certified by a third party, and it's so low because they don't ask the upstream suppliers, how do you produce? They look into a global database and say, well, BDO, where could that be? Could be at around 5, so that's the value that we use. So we are really struggling with transparency in this market. It's now there for PA6 and PA66. Everybody's fairly honest now, even if it's scary. But here we still lack that transparency. A lot of these numbers you cannot believe. Final 2 slides, okay? So if we use databases, we should really make sure they are up to date, use the most recent release, and that's a different thing, they should be updated regularly. If I buy the latest release, but the data are 10 years old, it doesn't help. They should differentiate between production routes, they should differentiate between regional fossil sources, and they should use real supplier data wherever that's possible. Final slide. This whole presentation is about the urge for more transparency. We are in the middle of this market. We try to bring transparency to it. We are calculating our own carbon footprints. We get the data from our suppliers, but we also face a lot of data in which we have a hard time to believe, and we just urge everyone to put pressure on correct data. And no matter how you source, you can source cheap and get a high carbon footprint, but don't fool yourself to source cheaply and believe in let's say, not transparent data. The whole industry needs to put pressure on it, get transparent, and then reduce the emissions. And with that, I'm done.
Thank you so much, Gregor.
You're welcome.